Okay, so let me show you the basic functionality of our spectroscopic software called massiveOES. So what you see on the screen is on the left side, you see the console or the terminal. This is not to be ignored because most of the error messages or warnings are really displayed only here in the left side of the screen. And here on the right you see the graphical user interface. So let me start with opening a file. This is here. So let's start with opening. This will be an OH spectrum. As you can see, CSV or TXT are both supported. So what you see here is the measured spectrum, and here we select which measured. This corresponds to several spectra that you can see in the file. That's why it's called massiveOES, because it allows batch processing of the data. You see there's really a batch of spectra. So let me go back to the first one, and when we try to process that, we would like to compare this measured spectrum with a simulation. So we should add simulation. So with the peaks around 310 nanometers, this is clearly a spectrum of OH radicals. So I will select the OH-AX database. Let's open that, and here it goes. So as you can see here, the green line corresponds to the measured data, the blue line corresponds to the simulation, and here in gray the residuals are shown. So this is basically the difference between the measurement and the simulation. And of course, if you just open everything from scratch, it looks pretty ugly like this. So let me first correct the values for the slit function. And because I already know something about my spectrometer, I would guess that it could be probably somewhere around 10 to -2, so I'll just correct these two numbers to get the right order of magnitude. Of course it's not exactly correct, but still it looks much better now. Yeah, well, second, I know that it was a microwave discharge in open atmosphere, so there I can expect really high temperature, let's say something about 4000 Kelvin in vibrational and rotational temperature as well. So I can change these numbers, and of course I have to press the update simulations button. Why? This is not something we were exactly able to control, because that's a bug in the user interface libraries that we are using. So always when you change something in this table, you always have to press this button. And it looks slightly better, but the intensity is still completely wrong. So what I will do now is perform my first optimization of parameters. So first I will just uncheck all these boxes, because I don't want to change these parameters at the moment. I will also uncheck these boxes because I don't want to change the temperature now, and just try to press this button. This is the most important button of the program, so I'll just press it, and you see it performed the first optimization. Now it looks much more similar to the measurement than it was before. Okay, the overall picture is quite nice, but the resolution is not very well, so I will probably want to zoom in. How to zoom in? I just go with the cursor to the part of the screen where the plot is, and I press shift and arrows. This is what the right arrow does, this is what the left arrow does, this is the up arrow, and this is the down arrow. I am holding shift the whole time, so basically you can play around with the spectrum like that. And maybe what you can observe is that the green thing is still wider than the blue thing. That means that I have underestimated my slit function, so I can do something like make it, I don't know, 4 times larger. And now I think that it fits slightly better than before. And I would also like to check the wavelengths. Well, at this moment the wavelength agreement is pretty well. This is not the usual situation, because when you start with the data measured from your spectrometer, it will probably be much more off. But if we go to higher wavelengths, you see that it's worse and worse. So if you want to make the situation better, there's a button called linearize. So I will press this button at the moment, and it makes a new window. And because I want the best wavelength resolution I can achieve on this screen, I will just maximize the window, and see, it's quite well, but still not perfect, especially here in the higher wavelengths. So we can start assigning the wavelengths that we consider equal. Here is the basic information how to use that. So I will just press the A, S and D keys at the moment. So you see, if I press A, I classify a certain position in the green line. If I press S, I make maybe the same position if in the blue line, and if I press D, it suddenly appears here. So that means I have assigned a pair of values that is considered equal. So I can do that several times. Basically, it should be done at least 3 times. So I will just... Oh no. Okay, I just made a mistake. So when we made a mistake, you can just correct it by selecting the pair of numbers and pressing delete. That will just remove the last point or one of the points that you have just selected. Okay, so S, D, and again A, S, D, and if we go to higher wavelengths, we see that now it's getting worse, so I have to correct more and more. And okay, let's do it like that, and let's see that if we can be satisfied with that. We just press the linearize button and see what happens. So now it's recalculated and it's slightly better. Yeah, so again the zoom functions with the shift and arrows functions here as well. So I guess this is the right pair. I press linearize once more. It should be straightly recalculated. Okay, here it goes. Okay, so now it fits well here in the end. Let's check if we just didn't destroy the calibration at the beginning, but I think that it's pretty well. So I will just send result. If you don't press this, you will lose all the work you have done in this window, but if you do this properly, you just send the result and you can close the window safely. So now, if you check here, you see that it really improved. So basically we have now the wavelength calibration. We have a pretty good estimate of the slit function, I would say, and there's some estimate of the temperature, but as you have seen, I just have written 4000, which is clearly not the best number that you can achieve. So we can now try to fit the values. So basically what I would always fit is the baseline, that's the vertical offset of the measured data from 0. Of course, you should always try to correct your measurement for all the dark currents and things like that, but usually still there is something left, so I would always select the baseline. The baseline slope at the moment I will just leave at 0, but if you have older spectrometer, it can happen that sometimes your baseline is tilted like that or the other way around, so in that case you will also have to enable that, but this is not our case, fortunately. Okay, the wavelength calibration I don't want to change at the moment because I think that I was probably better than the computer will ever be. The slit function for the moment let's just leave as it is, but we want to fit the rotational temperature and the vibrational temperature. Okay, we have changed something in the table, so I have to press this again. And then we can start to do the optimization. Okay, so now it's finished and you see that the residuals are smaller than they were. It's better. Basically the fit is much better than it was, and here we see the rotational temperature changed from my estimate of 4000 to slightly less. The vibrational temperature is also smaller than it was before, and here in the report I can also see the errors. So this is the third result of my fit. I know the temperatures, I know the errors, and if I'm really satisfied and I don't want to lose the work I have done so far, I could probably save my project. So I will just put it here, but I would put different ending into it. So you can do whatever you like, for example OES, so you just save that, and there it goes.